Hi everyone, this is Shao-Chuan. I'm going to present the homework 10, probability and stochastic, problem 1. So the Poisson process is defined by the following properties. The first one is the number of n of the points is a Poisson random variable with parameter lambda t, and the probability of n of t1, t2 is equal to this formula shown here. Number 2, if the internals t1, t2, and t3, t4 are non-overlapping, then the random variables n t1, t2, and n t2, t3 are independent. Third, at the time moment t, there is no more than one Poisson point. Using the point ti, we form the stochastic process x of t is equal to n 0t. So the first probability matrix is equal to this formula. The mean is equal to lambda t. The autocorrelation is equal to lambda t1, t2 plus lambda minima t1, t2. And autocovariance c t1, t2 is equal to lambda minima t1 and t2. For discussion, the mean of the Poisson process is lambda t, which is the linear function of t. It matches our common sense. The longer time we wait for, the expected number of buses is larger. The autocorrelation function contains a term minima t1 and t2, which comes from the property of the independent increments. The Poisson increment is defined as this formula shown here. So its first order probability matrix is shown here, and mean is equal to lambda. And autocorrelation and autocovariance has different results according to their ranges. So discussion for this Poisson increment is introduced to prepare us to define Poisson impulse process. It is increasing to see that in the expression of autocorrelation is a triangle with area lambda, which is independent of epsilon. When epsilon goes to 0, the triangle becomes an impulse with area lambda. The Poisson impulse process is defined as z of t is equal to derivative of x of t, where the x of t is Poisson process shown here. The property matrix is no definition. The mean is equal to lambda, and the autocorrelation is equal to, and autocovariance is equal, are shown here. So discussion: the process z of t minus lambda has 0 mean, and autocorrelation r of t1, t2 is equal to lambda delta t1 minus t2. That is, z of t minus lambda is a white noise. In the real world, there are some short noises, as in the figure below. We may define it as the output of a linear time invariant system with the impulse response h of t and impulse as an Poisson impulse process. The semi-random telegraph signal, the x of t, is defined based on the Poisson points again. The number of the points is a Poisson random variable with parameter lambda t. The x of t is equal to 1, either equal to 1 or minus 1, according to its even or not. The first order probability matrix is shown here. Again, they have two different values. The mean is equal to exponential of minus 2 lambda t. The autocorrelation is and autocovariance is shown here. Discussion: the probability is not 1 over 2 because we start with plus 1, and probability should be a little higher than 1 minus half. the probability goes to 1 minus half when t goes to infinity, which matches our expectation. The random telegraph signal, the y of t, is equal to ax of t. When the x of t is a semi-random telegraph signal, the first order probability is shown here, and the mean is equal to 0. And autocorrelation and autocovariance is shown here too. Discussion: the probability is equal to 1 of half. This makes us guess that y of t may be strict sense stationary. The expectation of y of t is equal to constant also makes us guess SSS. The random walk. Toss a fair coin n times. The k is equal to number of the heads in the n tosses. The mean is equal to 0. From the probability methods, we guesses that when n goes to infinity, we will have Gaussian density. The autocorrelation function contains a term minima t1 and t2, which comes from the probability of independent increments. The Wiener process. The Wiener process is equal to limitation of x of t when x of t is random walk. The mean is equal to 0, and the discussion, the omega 0 is equal to 0 with probability of 1. The omega has independent increments. Omega has Gaussian increments. The omega has continuous paths.